The Southern Ocean is considered the coldest place on Earth, and it should reduce life to its simplest and most minimal forms. At temperatures near 0 degrees Celsius, so cold that seawater avoids freezing only because of its salinity, energy becomes scarce, movement becomes costly, and survival should favour compact bodies that conserve every possible resource. In most ecosystems, that pressure leads to organisms that grow smaller and more efficient over time. But here, the pattern reverses. Life does not shrink, it expands. Sea spiders can reach over 60 centimetres, nearly the length of a human arm. Jellyfish can extend tentacles beyond 30 metres, longer than a blue whale. The shapes remain familiar, but their proportions feel strangely misplaced. Why does reality seem to extend beyond the limits we once believed it had to follow? At first glance, nothing about the Antarctic Ocean should feel unfamiliar. Water, darkness, silence, conditions we already understand. But as the eye adjusts, something begins to slip. Shapes emerge that seem recognizable, yet proportioned in ways that feel wrong. A spider-like form moves across the seafloor, its legs impossibly long, as if stretched beyond their intended design. A starfish unfolds, not in 5 directions, but in dozens. These are not alien organisms. They are variations of forms we already know, only expanded, exaggerated, and quietly defying expectation. The mind does not reject them outright. It hesitates, because what it sees is not impossible, just deeply out of place. Then, without warning, the ocean begins to reveal its cast. A massive squid drifts somewhere below the reach of light, its body thick, its colour absorbing the faint glow of anything that passes. Nearby, a spider-like creature walks on elongated limbs, each step slow and deliberate across the seafloor. A starfish spreads outward in dozens of directions, no longer confined to symmetry. And somewhere in the water column, a veil of tentacles extends farther than the eye can follow. They are all real, but for now, they remain unanswered. Scientists have a name for what is happening here: Polar Gigantism. In the coldest regions of the ocean, certain organisms grow far larger than their relatives elsewhere. The same species, the same biological blueprint, yet dramatically different outcomes. It is not a mutation, nor an isolated anomaly. It is a pattern, observed across multiple groups, repeating wherever the conditions align. The Antarctic Ocean does not randomly produce giants. It follows a rule, one that, at first glance, seems to contradict everything we assume about survival in extreme environments. So the question is no longer what these organisms are. It becomes something far more precise. What constraint has been removed that allows life to expand like this? And just as importantly, have we misunderstood the relationship between environment and size all along? Because if the coldest ocean on Earth produces giants, then perhaps the rules we trust are not universal, only local. The true boundary of size is not what we can imagine. It is what a body can sustain. For most marine animals, that limit is written in oxygen. Every cell depends on it, and as a body grows larger, the demand increases rapidly. In warmer oceans, oxygen dissolves less efficiently in water, creating an invisible ceiling that few organisms can surpass. Growth is not stopped by design, but by supply. Cells simply cannot receive enough to maintain a larger structure. What appears as a natural size is often just a compromise with the environment, and in most of the world's oceans, that compromise is strict, constant, and unavoidable. In Antarctic waters, that constraint begins to loosen. Near freezing temperatures allow oxygen to dissolve and remain in the water at significantly higher concentrations than in warmer seas. The difference is not subtle. It reshapes what a body can afford to be. Cells are no longer starved at scale. Tissues can grow thicker, structures can extend further, and the internal demand of a larger organism can still be met. It is not that oxygen becomes limitless, but that the margin expands. What was once a tight boundary becomes a wider field. And within that expanded space, size is no longer restricted in the same way. It becomes possible. In most ecosystems, growing larger comes at a cost. More mass means more energy, more movement, more maintenance. But in near-freezing water, that equation begins to shift. Cold slows metabolic processes, reducing how quickly energy is consumed at the cellular level. A larger body, instead of being wasteful, can become efficient, losing heat more slowly, storing energy more steadily, and operating at a pace that matches the environment. The balance changes. What would be excessive elsewhere becomes sustainable here. Size is no longer a liability to manage, but a structure that fits the system itself. And over time, evolution begins to favour it. Nowhere is this shift more visible than in the colossal squid. It is not simply a larger version of its relatives, it is a redesigned one. Unlike the translucent glass squids it descends from, its body is dense, muscular, built to retain heat in near-freezing water. Its deep red coloration absorbs faint, bioluminescent light instead of reflecting it, turning its own presence into shadow. Even its behaviour shifts toward ambush rather than escape. Size here is only part of the story. The entire organism has been reconfigured to match a world where cold changes every rule. On a tropical reef, a sea spider is almost forgettable. No larger than a coin, its body slight, its legs thin. In Antarctic waters, that same blueprint unfolds differently. The legs extend far beyond what seems structurally necessary, reaching outward like narrow bridges suspended over the seafloor. These creatures do not rely on specialized lungs. They absorb oxygen directly through their bodies, much of it across those elongated limbs. As the surrounding water holds more dissolved oxygen, the surface through which they breathe expands with it. The result is a form that looks exaggerated, but is in fact precisely aligned with the way it survives. In warmer seas, a starfish follows a familiar rule: 5 arms radiating from a central core, a geometry so consistent it feels almost fixed. In Antarctic waters, that symmetry begins to fracture. Arms multiply, branching outward in numbers that can exceed 50, turning a simple form into something dense and overwhelming. At first glance, it appears excessive, even distorted. But each arm is not decoration. It is surface, reach, opportunity. More contact with the environment, more access to food, more capacity to endure. What looks unnatural is simply a structure pushed further along the same logic, where survival favours expansion over restraint. Further up in the water column, the distortion takes a different form. The lion's mane jellyfish does not rely on mass or rigidity. Its body is light, almost absent, yet from it trails a network of tentacles that can extend beyond 30 metres, longer than the body of a blue whale. In warmer regions, related species remain comparatively small, their reach limited. Here, that restraint dissolves. Length becomes its own strategy. The cold, oxygen-rich water supports structures that do not need to be compact. What emerges is not a heavier organism, but a more expansive one, spread across space rather than concentrated within it. What emerges from all of this is not a single conclusion, but a layered understanding. Some elements are firmly established. Polar gigantism is real, and multiple Antarctic species consistently reach sizes far beyond their warm water relatives. Other aspects remain unresolved. The exact contribution of oxygen, temperature, and evolutionary history is still being studied. And some ideas can be set aside with confidence. These are not random mutations, nor evidence of unknown forces beyond biology. They follow rules, even if those rules are still being mapped. The uncertainty does not undermine the phenomenon. It defines the boundary of what we can currently explain. What unsettles us is not the unfamiliar, but the familiar pushed beyond its natural scale. A shape we recognize, a spider, a star, a drifting bell of tissue, remains intact, yet expands past the proportions our minds are built to accept. The brain does not register it as new, it registers it as wrong. This is where discomfort begins, not in ignorance, but in recognition without alignment. The structure is correct, the details are consistent, but the size disrupts expectation. It is the difference between seeing something unknown and seeing something known that no longer fits within the limits we trust. In cold, distant waters, observation is never complete. Light fades quickly, distances distort, and the surface itself bends what lies beneath. Early encounters with such environments were brief, fragmented, shapes glimpsed, then lost, details half-formed in memory. A long appendage becomes endless. A large body becomes immeasurable. Without stable reference, scale drifts. What is seen once, under strain or fear, is recalled with emphasis, not precision. Over time, these fragments accumulate, repeated and reshaped, not as deliberate invention, but as interpretation under limitation. In places where the environment obscures as much as it reveals, the boundary between observation and story becomes difficult to define. Rumours persist because they travel differently than data. Data requires context, verification, repetition. It moves slowly, bound to method and evidence. Rumours, by contrast, attach themselves to emotion, surprise, fear, awe, and those signals move faster than precision ever can. A single unusual sighting, especially in a place where few can return to confirm it, becomes resistant to correction. The mind fills gaps with pattern, intention, meaning. What cannot be measured is still remembered, but not accurately, only vividly. And once a story aligns with how something felt rather than what it was, it no longer depends on proof to survive. Not every mysterious account begins in error. Many start with something real, an observation made under difficult conditions, incomplete but not false, a shape glimpsed at the edge of visibility, a size misjudged without reference, a movement interpreted without context. Over time, what was once a fragment becomes a narrative, refined not by accuracy, but by repetition. Yet, within those stories, traces of the original encounter often remain. The difficulty is not separating truth from fiction entirely, but recognizing that they were never fully separate to begin with. In many cases, the unknown was not imagined. It was simply seen without the tools to understand it. In Antarctic waters, life does not accelerate, it stretches. Chemical reactions slow, metabolism settles into a quieter rhythm, and growth unfolds across years rather than seasons. Some organisms take decades to reach maturity, their timelines extended far beyond those of similar species in warmer oceans. The environment itself remains remarkably stable. Temperature shifts are minimal, pressure is constant, and seasonal variation is subdued beneath the ice. In such conditions, evolution does not rush. It refines slowly, preserving forms that remain effective across long spans of time. What emerges is not stagnation, but continuity, a system that changes so gradually it begins to resemble something frozen within time itself. The same traits that once made size and advantage begin to shift as conditions change. Warmer water holds less dissolved oxygen, narrowing the margin that large bodies depend on. At the same time, rising temperatures accelerate metabolism, increasing the rate at which energy is consumed. What was once efficient becomes costly. Tissues require more oxygen than the environment can reliably supply, and the balance begins to strain. A body built for abundance now operates at a deficit. The structure does not change immediately, but its viability does, and slowly, the very scale that defined success starts to work against survival itself. The first signs do not appear as sudden collapse, but as subtle shifts. In regions where Antarctic waters have warmed even slightly, maximum body sizes in certain species, such as sea spiders, have already begun to decline. The change is measured, not dramatic, but it is consistent. Individuals that would once have reached larger spans now mature at smaller scales. It is not an adaptation toward strength, but towards survival under reduced oxygen and increased metabolic demand. These are not isolated anomalies. They are early indicators of a system adjusting to new constraints, where the conditions that once supported gigantism are no longer fully present. What unsettles us is not just their scale, but what their decline implies. These organisms are not anomalies. They are outcomes of a system that once functioned with precision. As that system shifts, something deeper is revealed. The conditions that shape them are no longer stable. The unease does not come from their form, but from the realization that the world that made them is quietly disappearing. Taken together, the pattern is clear. These giants are not aberrations, and they are not beyond explanation. They are the direct result of specific conditions, cold, oxygen-rich, and stable over long periods. Remove those conditions, and the outcome changes. What remains is not mystery, but dependency, and within that dependency lies both their origin and their limit. It is not supernatural. Every form here, every extended limb, every drifting length of tentacle, every body pushed beyond familiar scale, emerges from conditions that can be measured, described, and tested. Cold water holds more oxygen. Metabolism slows. Stability persists across centuries. These are not myths. They are mechanisms.